And I ask y'all to make sure you make good notes because the book is kind of lacking on these sections right here. And we looked over what a sensor is. Everybody okay there? Yes. And we came up with a bunch of stuff that we figured that we needed to be able to sense. We looked at the push buttons. We talked about analog and digital. Are you okay there? I gave y'all an example of analog and digital. I think I fired up a ultrasonic sensor up here, which is analog. Then we was looking at position sensors. The first sensor we looked at was something called a potentiometer. Yeah, thank y'all. Something I forgot to do. So the first thing we looked at was something called a potentiometer. So this is a typical rotary potentiometer. So it's got three what we call leads coming out of it. And what we do is we connect an electrical voltage across these outside leads. Then when I turn the knob, which we call the wiper, then the voltage varies on this lead right here. I'll show y'all that. Can I show y'all that? One of these things operate? Yes or no? No. So this is a meter called, y'all get used to these guys. This is called a voltmeter. Well, it's actually called a digital multimeter. So actually it's got 3 meters inside of one unit. And then I select which meter I want to use. At least 3. This has got more. I select which meter I want. I select the meter with this knob. So right now I've got it set up to measure voltage. Yeah. Yeah, they measure at least voltage, current, and opposition or resistance. They measure resistance. So this one measures frequency. It measures a bunch of other things. But the 3, that would be optional for a meter, right? You understand? But to be a digital multimeter, they have at least 3 meters inside there: a voltmeter, an ohm meter, and a ammeter. Ammeter, A-M-M-E. So we call them amps, but the meter is called an ammeter. A-M-M-E-T-E-R, which is kind of strange. I don't know why they don't call it an amp meter, but they call it an ammeter. So I have a DC power supply right down here. And what I'm doing is I'm hooking it up to the 5-volt power supply. So this is 5 volts of push. And then this is my meter right here. And what I'm going to do is just take my meter and I'm going to hook it up to what we call circuit common. And then I'm going to take my other lead and just put it on this thing right here we call the wiper. What I'm going to do is I'm going to come up here and just turn the wiper and let me put it on a lower scale. Why is that called a wiper? It's called a wiper because the way it's designed. So the way it's designed is from a PowerPoint. So the way it's designed is that we got this center lead and it literally just wipes across the resistor. See that? And so for that reason it's called a wiper. So it's usually a piece of carbon film. Carbon is a semiconductor which works as a resistor. And basically we just do what? It just slides across the top of that. And what we do is we tap off a voltage between these two outside pins. So whatever I put on the two outside pins, it should be here and here. So what we're doing is we're putting 5 volts. Then I can get any, if the +5 is on this side, then what I can do, and if I make this my common, then I can get any voltage. If I move it this way, I'll get 5 volts. If I move it this way, I'll get 0. Anywhere in the center, I get something between 5 and 0, which is pretty neat. But what we would do, of course, is we would attach this.
Well, you're inducting it into a closed circuit, right? That's how it's created, right?
Well, you would used to, yeah. The output of the wiper is going to feed something. So I'm going to move the wiper. So right now I've got 5.4 volts. And I can literally get what? Any voltage between 5 volts and 0. So each voltage would represent, each voltage would represent a position of the knob. So instead of me coming up here and turning this, if I had it attached to something, then it would, that voltage output would be an indication of the position. Then we could run that into what we call an analog to digital converter, and I would get a number out that represents the watt, the actual position. It's pretty neat. So this is a potentiometer. We use these a lot. We manually control them. Until we got digital radios, this was the volume control on your radio. So if you got an old radio or an old TV, it used a pod. So we amplified it, and then we put it across the pod, and you had the ability to adjust the voltage that moved on down through the stereo. So, so it was.
So the more voltage you get, the louder it gets.
That was a fact. That's the way it worked. But it was the actual audio. It was actually the audio that we was tapping through there. So the actual. Those are power amps.
I hadn't had one of those in high
school. We built one and put them together. My son had a little S10 pickup truck, and we put one in his truck. You should have seen it. And I got a call that he had been arrested. He was in jail down in the city of Birmingham, investment, for playing his radio so loud.
Nice and play.
He was like, he didn't, huh? Well, this guy here, I think we had about. Yeah, if you're going to run those big old power amps, you need to crank the engine.
Yeah.
I've seen people have an extra alternator for the stereo.
Wow.
So they actually run two
Right.
alternators, one to run the stereo, one to run the car.
That's insane. Yeah. Dude, I got 2 alternators, man. My radio.
Now I had a stereo I bought when I was in Japan. It had about 400 watts.
Anything's happening.
Used to, well, it was, and it's up in the attic. It's up in the attic.
I bet it still works.
This car I had about 8 secret cord. I didn't know what it was.
Probably a subwoofer.
Did you work in the center?
I was in the Navy, but I worked on an airplane they called a P-3 Orion, which was an anti-submarine warfare plane. It's a big plane. So we flew everywhere we went. So we deployed to Japan. 6 months. I went over.
Like it over
Well, it was fun, but when you're away from
Right.
home, you're still away from home.
there. I've been away from home. Yeah, home and home. Imagine it's, I mean, what's culture like over there?
It was different.
All right. I mean,
Of course, I went to a lot of places while we was there. We from Japan, we deployed to all over the place. Even Iran. I went to Iran while the Shah was still in power. These are optical encoders. We looked at those, absolute and incremental. We don't have any absolute around here. All our robots use incremental encoders. And we looked at those, right? Okay there. Proximity sensors. Proximity means next to, right? You understand that. And we have several proximity sensors. We have what we call a limit switch. Limit switches have been around so long that they have the honor of having their own name. So they're not grouped in proximity sensors. So if you hear the term proximity sensor, normally these are your non-contact sensors.
They're what contacts?
Non-contact. And proximity means that all these guys are going to measure when something's at a certain spot, but they do it without touching the device that's trying to measure. The limit switch is a proximity sensor, but when we talk about limit switches, we call them limit switches because these were the first proximity sensors that ever came out. Everybody understand that? So if you hear the term proximity sensors, they're not talking about limit switches. They're talking about non-contact switches, which is photoelectric, and then we have magnetic, and we have ultrasonic. We have magnetic and inductive, capacitive, and ultrasonic. And we have every one of these on our manufacturing line. What we'll do at the end of class is we'll go over there and look at every one of these. Let y'all see the manufacturing line. So note, the term limit switch refers to the contact electromechanical device that senses proximity.
Go back one.
Wait a second. This is a limit switch. And you can actually see the contact, the connection to the contacts. So whatever's moving, when it comes up here and hits this, it moves this thing called an operator. Can y'all hear it click?
Yeah.
So the way these switches are set up is the switch is actually on kind of a pivot. So once you get past a certain point, it closes real fast and it opens real fast. Because the faster you open up a switch, the less opportunity you have of creating a lot of arcing, right? You understand? So this is the limit switch. This is a big size one. So this is called the operator, and we have all types of operators. But the device that we're sensing actually has to come up here and do what? And move it. Now it knows it's there. You don't know it's there, and now it knows it's there. Right? You understand? This is a limit switch. Here you go, Jesse.
Where would this go?
It would go anywhere I want to sense the position of something, but it has to mechanically have the contact. So they used to put these little switches in the seat of your car. Now they have a pressure sensor. It used to sense when you sat there, that decided whether the seatbelt light came on.
That's why I was like the application.
But now it's a pressure switch. Over there we're looking, we got a carriage that's moving across on a gear, and we need to know when it gets to a certain spot. But what it does, it just runs up against the limit switch. When it hits the limit switch, it stops because of that, but it also lets the computer running the program know it's at that spot. These are the limit switches that we'll use on our limit. So this is the limit switch that comes with the Lego robot. We get 2 of these.
We're gonna make a robot.
We're gonna build one, yeah.
Build one.
Yeah, so this is the limit switch. So this is Lego, so it's got a little that little star shape that they have. So you can put a lot of different operators on this guy right here. So So that would be, so what happens is it's got to make mechanical contact with what it senses, right? You understand?
Make a robotic car. So is this a programming unit?
It's not programming, it's a sensor that we
yeah, it's got the little, it's got the plug in there.
yeah, well, we take that to hook it into the controller. So this is the Lego controller right here. I was already on the camera.
Man, my kids have stuff.
So what we have to do is, so this is a sensor. This is an ultrasonic sensor. And what makes up a control system is we have sensors, and then we have a controller, and then we generate outputs depending on that, right? You understand? So what we have on this robot is that down on the bottom, these are input ports. So I have that cable that I use to connect this, and this is the computer right here. This is the controller. So what I will do is I'll write a program that makes use of this sensor.
This is Lego?
Y'all understand that? And this is Lego, so what can we do with this? Well, with this right here, we can use Lego and we can build nice little robots. Okay. And here's my limit switches right here. So what this is the operator, right? So if this robot's going to run into anything that's on the floor, it would run up against this. And then the program makes a decision on, hey, what do you want to do?
Back up.
What do you want to do? Yeah, but it's up to the programmer to decide what to do there.
Yeah, I'm actually a little robotic.
So watch it. So see if it comes up here and hits that.
Yeah, exactly.
But so the program, what is the limit switch do? So the limit switch hits that. And then it's up to the controller to decide what to do. And then we got another sensor.
Why is that? I should be
Oh, it's got a little, looks like that.
That's so cool.
So this is what's nice about Lego.
How much is this?
These Lego kits are around $300.
Really?
But it's a Lego, so you come up with your robot, right? You understand that? So this is a maze following solving robot, but it also can do what we call a free roam. So it just let it go around all, and it'll figure out how to get around.
So does it come up with? I mean, it does come with instructions just like every other Lego, right? I mean, like how to program it, like do you need a computer
And we'll look at that. This is the robot y'all gonna put together. Not this robot.
I'm gonna do this with my kids.
Now that's an ultrasonic sensor. So what it's doing is sending out a sound pulse,
Yeah,
and then it's timing how far it gets back. So what it's doing, every time it picks up something, it figures out which direction to turn. The program figures out which direction to turn.
Ultrasonics like RF.
It'll figure out the whole thing. So see, this is the problem we have is cables. So the ultrasonic sensor can't find cables, right? So that's what we use the limit switch for.
Wow.
That is so cool.
Something's in my way.
Grab the top.
So cool, man.
Yeah.
Design this program. I'm also going to try to modify it to follow a line.
It'd be cool to do that with like make up an Easy card, like card. Like that.
Limit switch. And then we'll look at the other proximity switch. The term proximity switch refers to the non-contact sensor. So what a limit switch has to do is a limit switch makes mechanical contact with what it's going to measure. And of course, as soon as I say, so it's an electromechanical device. Now, what's the problem with an electromechanical device is that you have two things that can fail, right?
Yeah,
It could fail.
mechanics or the
Yeah, it's just like a car. A car is electromechanical. So there's two things that can fail.
battery and alternator.
That would be electrical, or you could have a flat tire. That would be mechanical, right? So these are limit switches. They come in all shapes and sizes, depending on how much power they're trying to control. The more power they're going to control, the bigger they are. And that's pretty standard for just about all electronic devices. The bigger they are, the more power they can control, right? Are we okay? These are called electronic duty. These are called, these are your non-contact sensors.
What kind of like service industry, like maintenance work would you do where you have to deal with switches and stuff like that? Like, cause I'm sure there's some job out there
There are
where
all kind of jobs. Anything that you deal with manufacturing, you're going to deal with switches. Sensors. A magnetic reed switch. Contacts closed with the presence of a magnetic field. So what I'm going to do is, I don't know if I've got enough for everybody, but I'll make sure I get it back to you. Because I got to have at least one.
these are these are switches. So do those things in the center make contact, and then they induce a current. Yes.
Conduct. Conduct. Yeah, these guys sense a magnetic field. We use these a lot. They're not touching right now because they are called magnetic reed switches. This is like
Is this like can these fail? I mean, these can fail.
the other electromechanical.
So,
Yes. One of the things that we check a lot in with our meter is something called continuity. Continuity means there's little or no opposition between 2 points. So if I come up here and measure ohms, and we do this a lot.
this would be a test. One of these is bad if you've got a lot of resistance.
Well, no, you got to wait for. So right now, if I've got continuity, so this is my ohm meter. So notice right now it's showing I've got my meter leads apart. As soon as I touch them together, it says I have 0 ohms now, so I have no opposition. We use these to check fuses. Fuses are supposed to have little or no opposition. Circuit breakers are supposed to have little or no opposition. We do this so often that they've added something to the meter called a continuity checker. So if I put it on the I don't have it. I'm trying to show you what we're looking for. So this hold on. So the continuity checker, this allows us to check for continuity without looking at our meter. So if you put your meter on continuity and it beeps at you like that, it means we don't have to look at our meter to see if something's good or bad, right? You understand? So what I'm going to do is I'm going to take my reed switch now and I'm going to put it between my meter leads. So when it senses continuity, what's it going to do? It's going to beep. So is it sensing continuity now? No. I might have to find, I don't know if this little magnet will set it off or not. We'll see. No, it's not big. Let me find my bigger magnets. This magnet right here just isn't big enough.
Now, like, why don't I have a solar mount on for the battery?
Well, then you'd have to run wires outside the house. I don't know. Contact closes with the presence of a magnetic field. It has electrical contacts. The pros, it's watt, very cost effective. The cons, it's an electromechanical device. Anytime you say electromechanical, what does that mean?
It's electric and mechanical.
It means two things can fail.
So in this, the electrical is obviously where you connect it to the mechanical where it lights up.
Yep.
Machinery.
So these are reed switches. We have what we call mercury switches, which we don't see used very much. So we won't even talk. Since we won't look at that. This is basically the way they work. When I bring a north-south up there, then the north-south concentrates through those metals, creates a north-south, and what unlike poles do, they attract and causes the thing to close. And these guys have been around for a long time. There's some pictures right here. I didn't have to bring y'all. This is a typical fluid power pneumatic cylinder where they actually put magnets on the piston. This is very, very popular. And then what we can do is we can mount the reed switches out here on the outside. Don't see many of these in hydraulic systems. Normally on hydraulic systems they have to put it out here on the rod. But on pneumatic systems, since the pressure is so low, most of your cylinders are made out of aluminum. And aluminum allows the magnetic field to pass right through it, right?
Electric motors, they have magnetic systems. They're like this, that, like, alright, you know
A
how
piston
V8
is
has,
something.
you know how V8 has pistons and, you know, they go up and down and everything, like, an electric car, like, would it have electricity?
No, it's got electric
We got
motor.
something over in the air cylinder.
That's it. Yeah.
It's no-
Hall effect sensors. This senses the strength of the magnetic field. We can have digital or we can have analog. The pros are they're solid state. There's no moving parts. The cons is that we got to power these things up. So these guys will have 3 wires going to them. 2 is for the power and 1 is for the output. Predict. I can go. I'll need to go in. When we take a break, I'll get some of these. This is a Hall effect sensor right here.
Hall effect sensor?
See how tiny it is?
Yes.
But I don't know if you can see it or not. There's 3 wires coming out of it. We call them leads. So this guy here has to be powered up. So I have this connected up to my 5-volt supply. What we're doing on the LED is we're just trying to get an indication of when this thing senses something. So what I'm going to do is I'm going to bring my, oops. I need to get a bigger man. Oh, turn it so y'all can see it. This is what we call a latching Hall effect. So what it does is when I bring one polarity to it, it'll turn it on.
Are you using a magnet to turn on the light?
I'm using a magnet into a sensor, and the sensor is turning on the light.
Because the sensor closes the circuit.
Right.
That's cool.
This is what we call a latching sensor. So notice it sensed that, and I can approach it with the same pole, and it does nothing. I'm sorry. But what we have to do is we have to come in with the other pole. Once we turn it on, maybe I ought to do it like this. Once we turn it off, notice I have to turn the magnet around to turn it on. So it's doing it when I flip around. So this is called a latching sensor, and this is primarily the one we use. So if I come in here from the side, notice when I get to it, oops, let me turn it around the other way. it turns, oh crap. I need to get me a pair of needles. Now, once it's on, it's going to stay on until we flip.
Is that battery? What was that?
It's a magnet.
Battery?
A magnet.
What is it?
A magnet.
Yeah, I got it. From here, it looked like a hearing aid, right?
Yeah, this is a magnet. This is what we call a rare earth magnet, so it's very, very strong. This is just a regular. This is a bigger magnet. So when it sees one polarity, it turns on. When it sees the other polarity, it turns off. But once it's on, if it took a north to turn it on, it takes a south to turn it off. That makes sense? So notice when I move the magnet this way, it turns off. When I go on the other side, it turns on. So normally what we do is we go up here and so that's the way it actually senses the location right there. This is called a Hall effect. These things are really, really tiny. The advantage of them is what? Solid state, no moving parts.
So we see a sensor with 3 wires.
Well, no. All your photo optic sensors are going to have 3 wires on them. All your inductive sensors and capacitive sensors are going to have 2. It's just that if it's sensing a magnetic field and it's got 3 wires, it's a Hall effect. If it's sensing a magnetic field and it's only got 2 wires, then it's a reach. That's a good point. So we can look at diagrams when we look. So when we look at the actual wiring diagrams for these devices, so this is the class called System Diagnostics and Troubleshooting. So this is where we actually troubleshoot the lines. So see, these are sensors. This is a Hall effect. This is a magnetic reed switch. So notice this guy's got how many wires going to it? 3, even though they're numbered 1, 3, and 4. 1, 2. 2, we do have, and we're not going to explain that here. But as soon as I see these 3 wires, this little cradle right here tells me it's a magnetic sensor. So both these are magnetic field sensors. This only has 2 wires going to it. This has 3. So this is a Hall effect and this is a reed switch. That makes sense?
3 wire Hall effect.
Yeah.
2 wire
Is a reed switch. Yeah, because if it's Hall effect, it's electronic. Electronics have to be powered up. Hall effects are not powered up because they control the contacts with mechanics. Hall effects controls the contacts with electronics. So Hall effects have 3 wires going to the sensor. Magnetic reed switch only has 2.
What's the 3rd wire for?
How many? It's electronic. Electronics have to be what, Gary? Electronics have to be what? Electronics have to be powered. Electronics has got to have a power source before what it does works. So that would be like me going out to my radio and disconnecting the battery. So all electronics have to be powered before they work. Right? You understand that? So we got to have 3 wires. One of the wires goes to the plus DC. This wire goes to plus DC. This wire right here goes to minus DC. That's power. And then 4 is the actual output of the sensor, which goes back to our controller, which over here is a PLC, which is the programmable logic controller. Now, when I said all solid state sensors have to be powered, that wasn't exactly true. Inductives actually power through a load because they required so little current to operate. So if I know it's a magnetic sensor and it has 3 wires going to it, it's going to be a Hall effect. If it's only got 2, it's going to be what? It's going to be a reed switch. So this is the Hall effect I just showed y'all. Very, very small. Photoelectric sensors. Photoelectric sensors do exactly what they do. They detect an object by using some form of light. Right? Everybody okay? So we have 3 basic types of photoelectric sensors. We have what we call a through diffused. We have what they call a retroreflective, and we have what they call through the beam. So the blue is the object that we're detecting. So notice what the diffuse does. The diffuse does what? So here's the object I'm detecting. When light hits a surface, what happens when the light hits the surface? It reflects, depending on the color, right? You understand? So that's what a diffuse does. It depends on reflective light off the object itself. Y'all understand that? A retroreflective, we have a device called a retroreflector. Anybody ever seen a retroreflector?
On bicycles.
Bicycles. Well, we put a lot of them on trailers. We have a ton of them on cars. What does a retroreflector do?
And it gets light, it lights up.
What a retroreflector does is that the problem we have with using reflective light. So let's say I use a mirror. A mirror is really, really reflective. But the problem is if my light is not lined up perfect, and it hits this, and I'm standing back here, then I'm not going to see anything.
It captures the light.
Sort of. What it is the retroreflective is made up of little tiny triangles.
So they're all bouncing off.
And what happens is that when you hit a retroreflector, it wants to do this. Come back to the source. And that's what the triangle shape does, right? You understand? And like you said, if it's not here, it'll bounce off another one and then do what? Come back to the source. Now this is over a certain angle. So, but what's nice, as long as you're within that viewable range, it reflects back to the source. So that means the light does not have to be perfectly aligned to come back to the receiver. But it works like this. So what happens is here, this guy is looking for light. This guy, if it don't get reflection, it knows the object is breaking the beam, right? Don't understand that. So what a diffuse does, it depends on light being reflected off the object. What retroreflective looks at is the light being broken coming back from the reflector. So if the light is broken, then it knows something's there. If the light comes back, it knows something's not there, right? You understand? Now, what would be the problem with all these? Well, and then we have what we call a through the beam. Through the beam, we have a separate transmitter and a separate receiver. And then we shoot the beam between the transmitter and the receiver. But it's still looking for the object to break the beam. So if the beam gets broke, it knows something's there. If the beam don't get broke, then it knows there's nothing there.
So what would you use that for, like plumbing?
What would I use plumbing for?
Like,
So I'm working in an automated manufacturing facility. And so that means basically almost everything's automated. Well, a lot of times if a robot wants to pick up something, it's got to know something's there before it picks it up, right? Okay.
so it sends out a signal to see.
Says, okay, I'm here, and then the robot's been sitting up here perched. So the robot sits up there perched, not doing anything, because it's waiting on something to be there, right? And the problem with automated manufacturing is sometimes we have gaps between, so I can't do it timed, right? You understand? Because I might have a gap.
Sensory.
So we have a sensor out there, and it breaks the beam. And once it breaks the beam, or if it don't get reflection, or it gets a reflection back, depending on which type of sensor it is, then our controller knows something's there, and then it can spring into action. So the function of sensors, of course, is to make things automatic. Right? You understand that? To automate things. And the more automation I have, then the less people I have to get in there to do this stuff.
Which is what people are paying. And you're only paying
But-
one time, which you're paying.
So you're not paying these, U.S. Steel, we call them laborers.
You're paying.
So you're paying people to do something that I could do automatically if I had some means of sensing when to do it, right? You understand that?
Right.
Yeah, you put some guy out of work that you are paying minimum wage, and then you hire another guy like me that you're paying a lot of money to come in and keep all this automation going. But what they're doing is they're replacing these unskilled laborers with skilled laborers, right? You understand that? So I use less people,
But
right?
you're getting more done.
You get, yeah, because your machine, you're getting it done more accurately, but you still got to have somebody that does what?
But guess what? The world's
You
running
still
out
gotta
of
have-
food, the world's running out of antibiotics, and you can't make that. I mean, you can, but where's it come from? Yeah, we're running out of antibiotics.
Yeah, we're running out of antibiotics because they want to raise the price.
That's why we're taking this job someday.
Yeah, fixing these things. So the more and more, and you're going to see this happen, is more and more we're going to move toward automation.
Everything shifts towards automation.
But the problem is, and thank God for automation, because if it wasn't for automation, cars would still be foreign cars. Y'all understand that? So how many jobs does Mercedes have in them? 3,000?
Mercedes is German now.
Yeah, but it's still,
Yeah, it's here.
it's still, the cars are made here. Now, why aren't they not made over there and shipped over there?
Because it's
Because now it's more expensive for them to make the cars there
Right.
than to make them here because of automation.
That's why Mercedes, they don't cost that much.
Well, it's not that they don't cost that much.
They don't make them over there no more.
They don't make them over there.
They don't
Well,
make
they
them
do
like they
make them
used to.
over there, but now they make them all over the world. There's no telling how many Mercedes plants there are. Used to, when they first started, Toyota first came in and Nissan, there was no Toyotas made here. There was no Hondas made here. There was no such thing as Hyundai. So,
Right.
because what were they doing? We call them foreign cars. Now, why did we call them foreign cars? Because they were making them in Japan, they were making them in Germany, and then loading them on these big old boats and doing what? Shipping them over.
But they overcharge that. They want to,
Well, everything's expensive. You say when they expensive. Yeah, the first job I was making $3 an hour, and I thought that was a lot of money.
How much?
Right, you understand
How
that,
much
but
you
this was
making
back
now?
in the 60s. Now that same $3 an hour would probably be like $25 an hour now.
Right. Directors?
Career tech officer,
Who are you looking for?
career tech officer.
We have an assistant dean of career tech
like, sort of like Yugoslavia. I thought, well, I'm not about qualified here. I just didn't know.
Yeah, but what you got to understand, cars are still like that. But when you compare to what they are now to what they were then, what's nice about it is that we wouldn't. How many car manufacturers do we have in our area that would be used to be considered foreign cars?
Jaguar.
No, in Alabama, in our area.
Fiat.
No, not in our area.
Oh, in our area?
Toyota, Honda, Hyundai, Mercedes, and why? Because now it's cheaper for them to do what?
Build it here and.
Then, right? Because of
It's good for Alabama.
automation. But because of automation, right? You understand that? So people keep saying automation takes jobs, and it does. But the jobs that they're taking are what we call unskilled. By the way, people, they're starting to make robots that flip hamburgers.
Yeah. Word? Yeah.
That flip hamburgers.
Yeah.
That cook and make hamburgers.
While we're on the subject,
They're going to be getting rid of all that
Essentially-
$15 an hour.
essentially after this course, getting my AC degree, what kind of a entry-level job can I expect to get, or what kind of money
70, 60,
range
70.
are we
Sorry.
talking?
Automation.
We're talking around the $50,000 range for a job. Nancy's done a really good job on posting that information. I think she's got it on
Oh, really?
on our website.
I hear
Maybe
a lot about
different.
Mercedes, but like what other kind of what? Just in general, I know they're
Well,
everywhere.
we talk about Mercedes for foreign cars, right?
For example, before you go further, I did my little report thing on those bartenders because I was in the food industry for 30 years. So I did mine on bartending in restaurants. So they both a cooking one and a bartending one. Because they would take my job, you know. And is there somebody on that boat that has to be able to be ready to work on those robots that are on the ship, cruise ship, where all the bartending? You
Now,
know,
what they probably do there is on those, I doubt there's somebody on the ship that fixes them. Probably if it breaks on a cruise, they would just decommission them and bring a human in there. But sooner or later, they're going to bring that ship back and somebody's going to fix it. Somewhere.
So the job range as far as like an entry level degree holding AUC, 50 grand median, Mercedes. That's
No,
why I-
no. Mercedes, you got to understand, Mercedes is an assembly plant.
They're not making the part.
There, so we got Gaston, we got Flaxen Gate, we got Plastech, we got all these tier 1 gas stump, all these different tier 1, we call them tier 1 manufacturers. These are the people that most of our people get jobs with. Mercedes, it's very hard to get into their technical program there. Because what they do is that, first of all, they have an internship thing set up with Shelton State. And so what you do is you get an associate's degree, and after that you go through another 18-month program. If you're in the upper, they came and explained it to us. Certain percentile, they'll go ahead and put you through the 18-month training program. And then out of the 18-month training program, I think they said 25% goes into maintenance. But if you can get into the 18-month training program, then you're guaranteed a job. It's just that if you don't get in maintenance, you get in production. We have an internship set up with Groves. And then we're working on an internship with Honda. And then we have 2 more companies, CNC Steel and Amerex. Amerex is looking for an internship program. Those programs are 3-year programs. We had something that happened this last semester that hadn't happened at all. It looks like Mercedes is having a pretty hard time filling people from Shelton. So they hired somebody right out of our school. They hired somebody into Mercedes out of our college last semester. This is the first one they've actually hired without going through any of their company.
I was offered a job, but Mr. Holloway had a job to start a robotics program here. And it was $17.50 an hour, entry level training, insurance, all that stuff.
That's good.
Does that sound?
1750 for starting off.
Or starting, yeah.
Before all that,
None, but you gotta understand our employment rate. With all this automation, what's the employment rate now for the United States? What's the employment rate for the average employment rate for the United States?
Does that mean how many people are employed as opposed to how many are not?
68.
Yeah. What's the percentage? Alabama's down to like 4.2%.
What?
Yeah.
4.2% is full
For
employment?
people that want a job. Huh? So we're talking about even with all the automation, the employment is really good, but now what they're looking for is they're looking for their skill.
And if you wanted to do something in research, like the surgical robots, and learn more in the medical field, or research not medical field, I take that part of it. But there are robots that do that work. How do you get into that?
Don't know. We don't.
know.
CMC. CMC is over by the airport. Over by the airport. They do structural steel. So, guys, we need to move on. Through the beam, y'all okay there? Any questions? Now, what would be the problem with these guys?
Earthquake.
That's the problem with everybody. Misalignment could have problems. Retroreflective is really forgiving as far as alignment goes, but this through the beam is not forgiving. So if you got knocked off, you'd have a problem. We have a problem with dirt, right? So these guys are not really good in extremely dirty environments. You probably see 1,000 of them down at Mercedes. You won't see any of them at US Steel, but it runs. Another problem we have is that they won't detect transparent things, right? To understand that. So if I wanted these, I wouldn't use these things in a glass factory.
No.
To detect the glass. But we have stuff that does. This is retroreflective. So we have a retroreflective that we mount somewhere. So if you go into the college bookstore up there, you go through a retroreflective sensor. It's what beeps. It beeps when you go. You look on one side, you'll see a transmitter receiver. On the other wall, you'll see a retroreflector over there. This guy, the big advantage of this one, this has the ability to have the longest range. Because when I use a retroreflector, it's depending on the light to travel to the reflector and back, right? You understand? Yes or no?
Yes.
That's what those it goes, it's going through it, but it really don't go through it.
No, it don't show go through it. Yeah, it's showing it's getting blocked. Here comes the light. Here's the transmitter. It hits this device right here. The light is still being right, you understand? And what's it depending on? So right now it's being blocked. So I know what you mean. This dashed line means when it's clear. Just like this one right here. So down here, that dashed line means if it's not there, it reflects back. Understand? Yes or no? So it's not going through it. This is a diffuse sensor. This guy here probably has the shortest range because it's depending on reflective light off the object itself. And what determines how much light reflects back off an object itself? What determines how much light reflects off an object itself?
How much light? Without.
The color, right? You understand that?
What? White, red.
Yeah, so white reflects all light, right? You understand? Black supposedly reflects no light, but there's almost no such thing as pure black. You use that term a lot, but it almost absorbs all light, right? So that means if I come up here and I have a black object, it's going to be a little hard for this guy here to detect. It likes to reflect a lot. Okay. So this is a diffused, but we can use this thing to give us a sense of color. So normally what we do, when we can't see it, normally these are digital sensors, but the light detector is actually analog. So inside the sensor, we have an A to D converter. And normally what we have the ability to do is we have the ability to set what we call the threshold on when it actually switches. So we can adjust these things to see real bright colors, but then when they get below a certain color, we can't see them anymore, right? Does that make sense? And we'll see this when we go over there and look at the manufacturing. So what we'll do is we'll see they're using a diffuse sensor, and they've got it adjusted so it don't see black. And then while it's assembling these cylinders, it assembles a black one different than it does the other. This is one way that it knows. So we'll see on just about all these photoelectric sensors is we have the ability to set what we call a threshold. The diffuse sensor is very, very popular. Are you okay? Okay, guys, y'all go ahead and take another break. Keep in it, right? Proximity sensors and also limit switches. So we saw some limit switches over there. We saw through the beam, we saw retroreflective, and we saw diffused, right? And now hopefully that gives you a little insight of what's going on, right? If I'm going to do a lot of automation, then we're going to have a lot of sensors. And I think I heard Alfonso say that where he works at, they don't have any robots, but they got a lot of sensors, yeah. Tons of sensors.
So I don't know how that blends in that they got PLC.
Well, PLCs is, so a control system consists of three main systems. It's got inputs, which are our sensors, and then it's got something called a controller. So the controller takes the input from the sensors and decides what to do with outputs. Does that make sense? Well, a PLC is the controller, but the P in PLC means it's what? Programmable. So literally every one of those PLCs on the Amatrol line are running a different program. But those programs can be saved on a different device. So let's say one of my PLCs go out. Well, I don't have to keep 10 spare PLCs. I can keep one. And then what would I do? I just put the program in it for that module. I go out there and swap that thing out. I want to change the time for a timer. We can access these things through a network. So, I mean, we can literally do things from Germany to my plant over here in America, because if it's on the internet, we can do things like that, which you just can't do with other controllers. So when I first got into the field, all the controllers, they were not programmable. They did what they did, and that's all they did, right? You understand? So the problem is it was less flexible. But now I've got a PLC that instead of me going out there and tearing things up, if the PLC is bad, I just do what? Pop a new one in there. What's that? Luckily we haven't. We're going to teach a class. It's called Advanced. I don't know the name. And what we're going to do in that class is that we're going to take the Festo line and change it over to Allen Bradley. I'm sorry, we're going to take the Allen Bradley, change from Allen Bradley to C. So we'll go through the whole thing. That's long. It is. And like we said, it's going to be interesting. Who's going to teach the class? That was the optical interrupter. This is just another type of through the beam, except the transmitter and the receiver are in one unit, and the spacing is set up by, when you buy these things. You see, this is the optical interrupter was used on the traverse or the sorting station, the last station over there. It was used on there. Oops, wrong way, guys. So we got two other sensors we need to look at: capacitive and inductive. These are usually called solid state limit switches. So if you hear that term, it's solid state. These are your capacitive and your electric sensors. They have no moving parts, no physical contact with the items being sensed, can be operated in dirty environments. Capacitive sensors can be obtained to sense solids, liquids, and gases. Inductive sensors sense nothing but what? Inductive sensors sense nothing but metals. Have y'all been exposed to an inductive sensor today? Where? Before you got here. Used to, in the old days, all your red lights were timed. So they were timed. So used to going up the Vesper Superhighway, if you made the first one and you went 40 miles an hour, you'd make every light all the way to Bumpus. Because they were all timed for 40 miles an hour. If you didn't go 40 miles an hour, you'd get stopped all the time. So there was a big incentive for you to go the speed limit up the Vesper Superhighway. Now we don't do that. Now we have inductive sensors all over the place. So when you pull up on a red light, that big old coil you see out, that big old loop thing out there is a big old inductive sensor. And what's it doing? It's sensing the what in your car? The metal in your car. No, it's not sensing the weight. It's sensing the metal in your car. It's an inductive sensor. So that's a perfect example right there of using a sensor to trigger an automated system. So now our lights are automated, right? Most of them. Unless that sensor goes bad. And then you'll end up with this one out here that turns left into the college. It comes on all the time. So no matter if there's a car there or not, the lights will turn red, and then this left, and the left turn light will come on. So y'all watch that. It happens all the time. Why? Because that sensor's gone bad, and they haven't come out and did one. I don't guess nobody's complained about it. But capacitive sensors can be obtained to detect solids, liquids, and gases. So a lot of your smoke detectors work off capacitive sensors. But inductive sensors sense nothing but metals, which is very, very, so if you got a metal detector, that's an inductive sensor that people go out on the beach and look for stuff. But that's not digital like the ones on the line. So these are capacitive sensors. We have two types. One's called shielded and unshielded. We call these bulkhead mounted sensors. Come from the old Navy days. So in the Navy, you call a wall a bulkhead. I'm not going to tell you what we call the bathroom. Now, we call the bathroom head. And in the Navy, there's no such thing as stairs. Everything's ladders. And then we have port and starboard, right? Fore and aft. So these are what we call bulkhead mounted sensors. This is called a unshielded sensor. This is called a shielded. Can y'all see the difference?
Yeah.
So notice here, the sense here is mounted flush with the threads. Here, the actual sensing element extends out past it. These guys here would be more selective than these. These would see things over a wider range, where a shielded would see things over a very narrow range. But what will these guys sense? Capacitive sensors, what will they sense? Solids and liquids and gases. Normally we don't. It does this by, in AC you'll learn this formula, but what in a capacitor, what determines its opposition is what we use as an insulator. So what happens is when we start moving objects within this range of this thing, it basically does something to what we call an electrostatic field. So knowing this is not important. All you need to know is capacitive sensors. What can capacitive sensors sense? Liquids,
Air?
solids, gases. So we'll show you all a sensor over there. It'll pick me up. I'll just put my hand out there. It'll pick me up. Then we have inductive sensors. Inductive sensors sense metals. You wasn't hearing me, Christine, but all these traffic lights now have inductive sensors on them. And what do they sense? They sense your car. And they have a sensitivity adjust on it. Used to, when I rode my motorcycle, if I was trying to leave the front gate over there, it would never trip. Because my motorcycle didn't have, well, these guys don't sense weight, they sense metal. So I could have a semi truck made out of plastic and they wouldn't sense anything. So y'all understand inductive sensors basically look for metals. It senses ferrous metals better than it does non-ferrous metals, but it will sense aluminum. It just don't sense it as good as steel. So when you pull up to a red light, you see that thing in the road, if it hadn't been paved over, that is an inductive sensor. And it's sensing the metal in your vehicle. So that's why they can come in like the left turn light down here that you turn and get on the interstate. If you don't have two cars sitting there, the left turn light won't turn on. It'll turn green. Why? And then on 280 now, those turnarounds, if one car pulls up on the turnaround, it don't do anything until two cars get up there. So they have the ability to set the sensitivity on those inductive sensors, but they're looking for metal. So a lot of things that we sense is metals, and we'll look at these are several of these on the system. Other sensors, ultrasonic, we've already looked at that. Distance sensors, ultrasonic, and then photoelectric. We've already looked at this. That was the first thing we talked about. Do you have any questions on that? I rearranged the PowerPoint, by the way. Are we okay? This is the well, one sensor that we didn't talk about that the Lego robot has is the Lego robot has this sensor right here. What does that kind of look like? Kind of looks like a microphone, right? So this is a sound sensor, which we might run into. So when y'all do y'all's programming on your robot, this is the way you're going to start your program, by making a sound. This is the optical sensor, photoelectric. This is a diffuse sensor. So when we turn it on, one of the light comes on and then it looks for it to come back. We can program this to do what they call an ambient light sensor, so we can tell our program just to look for light, the intensity of light, or we can do it to use it as a diffuse sensor. So what does diffuse sensor senses on? Sense? So what's the three times? Through the beam. What is through the? How does the through the beam work?
If it's clear, and then it'll pass through, but if it comes back.
Well, it don't, on through the beam, it don't come back. It
Yeah,
breaks the light between the transmitter and receiver. So through the beam does not depend on reflected light. It literally breaks the beam, right? So we have a transmitter, we have a receiver, they're mounted back across the thing, and then the object would move between the transmitter and the receiver. When the object moves to there, it breaks the beam. And that's why it's called through the beam. How does a retroreflective work? So how does retroreflective work?
It relies on reflection.
Bounces off a reflector. And the name of the reflector is a retroreflector, right? You understand that? We can buy these vests. A lot of bicycle riders ride them that are retroreflective. Most of the lettering on stop signs is retroreflective. So what happens is, even though you're not lined up perfect with a stop sign, it reflects back to you, right? And then the diffuse, what does the diffuse do?
Diffuse is, you go through it.
Diffuse means we're actually doing what we call reflective light. So what it's doing, it's actually looking for the light being reflected off the object we're trying to detect.
So there's that thing in there that is going through it. Like, picture that there, right?
Now this is a diffuse detector right here. So what we got is we got the transmitter and we got the receiver in one end. So what one light does, it turns on, shoots the light out, and then when it hits something, it reflects back. Right? You understand that? I'll show you my robot. The battery was dead in my robot. I'm charging it. I'll show y'all one of the programs you're gonna have to write is or you're gonna try to write in the competition is to drive a. No, it's not a golf ball. It's a plastic ball. So what you do is you turn on your diffuse detector, and then you start running the robot until it gets up and sees the reflection, right? And when it sees the corrections, you tell the program to swing it off, and you see how far you can run. Then we've got a program you'll write where you're going to make the robot follow a line. Well, how's it going to know where the line's at?
Got a sensor.
With what type of sensor? Diffuse sensor. That's exactly. So what we'll do is we'll turn the diffuse sensor on, and we'll use white tape right here. And so what when we say follow the line, it's not exactly true. What it's going to do is follow the edge. And we're going to run it off this gray floor. So the white tape will get a lot of reflection. The gray floor will get very little, right? So what our program will do is look at it. So we'll set a false when it sees gray. We'll set a true when it sees white, and it'll follow inside. That's it. So the only real detector, the light detector, the Lego robot we had. Now the new robot, they call it the ED3, the Mindstorm robot. It has a color detector. So it's literally got three. It shoots out a white light, and it's got a red, green, blue lens that it picks it up on. So guys, we're almost through with this. Somehow I got way back here. Oh, I'm on the internet. On the email. Nope, that's the internet. Where's my PowerPoint at? Right there. This we've already looked at this. This is where the pop potentiometer will be used to measure height and then pressure. So one of the things that sets the amount of force that a fluid generates is the amount of pressure we have, right? What's the formula for force? Yeah. Force. So what is a force?
It's
A force is a pressure that tries to cause something to change direction, right? So the amount of pressure we have would determine the amount of force that we have. So pressure is very, very important, right? So over there on our vacuum system, when that thing came down, how did it know when the vacuum came on? Well, it used the pressure switch. indicate the pressure, either it was there or not there, right? Understand that? The all these other robots, if I went over there and if I went over there and wrote a program and told it to close the gripper, the program would close the gripper and it'd have no idea the gripper didn't close at the pressure level. Over on the KUKA robot, if you don't have the pressure turned on, it won't let you do anything. So that means there's a pressure switch in there, or a pressure sensor in there, right? You understand that? So we have all types of pressure sensors. We're not going to get into the different types. And we have analog pressure sensors and we have digital pressure sensors. So what would be the difference between an analog pressure sensor and a digital pressure?
Analog, you have to read it.
Well, an analog would show us what pressure was there. A digital would just say either the pressure was there or not there, right? The difference, this or that.
Digital says it's either there or not there. Analog says what?
Analog gives us the value. Digital just says if it's there or not there, right? Understand? So you got a fuel gauge on your car. Is that sensor analog or is it digital?
Analog.
It's analog because it shows you how much gas you got. Now, every once in a while, you got a need fuel or you get a fuel light that comes on. That's digital. My wife's got a light on her van that comes on when the tire pressure is too low. That's digital. You don't show her how much pressure is there. But then she's got another one that shows us that actually reads the tire pressure. So she can read the tire pressure from inside her car, inside her van. So the tire pressure sensor would be analog, right?
Mm-hmm.
But the one that says she needed to put air or take air away would be digital.
You still think pressure on the car, pump the tires up too.
Some of it, some of it.
I'm sure some of them do.
Well, yeah, some of them.
Those high class.
You can get a Harley, one of your big Goldwing motorcycles has a built-in.
What?
And you got cars that's got those air shocks in them.
Uh-huh.
I could have used
Air
that.
rides.
I had an Expedition big van that automatically kept the rear end at the same height. So if you hook your trailer up to it, you hear the compressor cut on and it keep it the same.
But,
Until it went bad and then
Yeah,
it started.
I had a Cadillac like that. And with the brush, and something went wrong, it just squatted. And I drove her and jumped and something like that.
Oh, really?
I mean, I didn't have enough money to fix it.
Yeah, I know. Those things are nice, but
expensive to fix. Very
Yeah, I had a car, it had all four tires showed up. It showed pressure.
yeah, that's what my wife's fan does that. But then she still's got a digital that comes on that tells us when she needs to add tire. Add pressure. What's that? No. If it is, I don't know about you. If I'm not saying it wasn't that, I just hadn't heard about it. And then we have temperature sensors. This is about all we need to talk about in this class. So guys, y'all got any questions about any of these sensors? Let's just look at the rest of them. We have temperature sensors, which is very, very important. So as a temperature sensor in your car, some of y'all have analog temperature sensors, right? So just about every car has got a digital sensor that indicates when your car gets too hot. Some of your cars have analog sensors in it that actually shows you the temperature of the water. We have different methods of measuring temperature, but we won't get into those. We got a class called Sensors. And if you take the Sensors class, we'll go into a lot more sensors and go through this class. here we're predominantly looking at basically the sensors that we use in robotics. You can see the function of these things, right? So what do? Well, they let the control system know if things are there, if they're not there, if they're at the right height, the right size, what position they're at, and all this other kind of stuff, which is really, I don't know. I mean, even we can sense equilibrium. By the way, since my wreck, I have a report, stuff like that. We have gyroscopes now that can sense equilibrium. There's one of the guys at when we went to Germany and was going to the level 2 school, he had made a Segway out of the Lego robot. So it used the gyroscope though. You can get a gyroscope module for these robots. You can just the Lego robots, the number of sensors you can get GPS for these things. You can get gyroscopes for them. You can get all kind of neat little things. By default, they support these 5. They have an ultrasonic sensor, they have a sound sensor, they have a light sensor, they have a limit switch. They have 2 of those. So we all okay? Well, if they don't have a sensor for it, then it would be surprising to me that somebody wouldn't come up with one. Because all it's doing is taking a physical stimulus and converting it over to, so vision systems, we never thought vision systems would come into play, but now these guys can see.
I got a sense that I'm doing okay. You know what I mean? Other than, like in the medical.
We are leaving, by the way. That's all we're going to do. I got a conference call here.
I got to go to work.
Yeah, I know. I got a conference call. I got to do. And it's a good spot. It's a good place to stop in.
Okay.
I'm supposed to go on a conference call at 12:30.
Oh, super
No.
distracted.
Yes. I'll try to get that new,
The program, right? The program. This is what you do. This has to start with turn it on. That's what you need to do. And now, look, the thing is, what you had up there,
well, I'm not going to give you the program. I'm not going to give you the program.
no, I don't want that. I just want to know the I thought maybe this robot over here was like the name. The robot that was up there. Yeah. That's not the name.
That's not the name of the robot.
It's just kind of
Digital I/O. Digital I/O. Digital I/O. What to do is you can program digital I/O. Number 15.
turn it on.
What's up the name?
I know.
This is all the things. This is all the things that we use.
Yeah, no, I'm not going to. This is what I want. I want to turn it on. I want to move forward.
Okay, what you need to do is follow these instructions in the cloud, right?
I have this. I know.
It tells you all these, it makes you look these things up, and you call these things up inside the write down the name, feedback,
This is not in what I'm doing. Go ahead and talk. It is not.
in that lab, you got the lab?
Oh, yeah, at all the things. I got the right, yes, but if I go to, if I go to the,
Oh. Okay,
I
I
don't
was,
see that time.
yeah, I see it. I really came up. Yeah,
You bought this.
No, I was going to see if you have a no, I wanted to sign it off. I know not to.
Oh. Yeah, I've read it.
Okay, so I know, I know exactly, so if I go through and I go like, and I come over here and I go.
Well, I do. Here. Anyway, I might have went to it. So that's what
Not okay. Because how you want it, not okay. We don't believe them on the I was thinking out of the
yes, yes.
So what we got, he said it's hard to know. He said we got, that's what, there's something like,
Yes. This is the way I went.
that's the same thing. I don't know what it is. All right now.
Other on this. I like.
Oh, this- This is what. Yeah.
Oh, yeah, but it's all from our record. We don't need to learn all that. We could probably take the whole national program, but we don't have time. So all we do is just to follow, just to give you a feel of all our program. They'll move to this. As soon as, in fact, we'll move to this guy before y'all move to this. Because we've only got one of them. What they'll do is they'll give us a chance to flip them.
Not, not at all.
No, but this Friday, I'm not going to be in the meeting. Next Friday, I will be in. I don't know.
Well,
I know, but
I just got a fiddle fast.
problem we have is we schedule all our office hours on Friday. And what do they do on Friday? They schedule all our meetings on Friday. So that's what they do with them.
You know, meetings get in the way of real process. Okay, thank you.
Well,
coming over here?
I'll take your off on this over.
should have been 80.